Good afternoon, dear colleagues. We are presenting our report, The Possibility Investigation of Block Algorithm Construction Using the BPM Method. Report authors Dmitry Lvovich Golovashkin, Image Processing System Institute, branch of the Federal Scientific Research Center, Crystallography and Photonics of Russian Academy of Sciences. David Kalachan and Lyudmila Yablokova, Samara National Research University. The development of computer optics combines the field of computing and optical technology, is usually associated with simulation improvement in the method of production of optical elements and methods for their calculation and analysis. A improvement method among a latter is the beam projection method, in particular the BPM method based on the fine difference solution of the Helmholtz equation. Fine difference beam propagation method in approaching a slowly tangent envelope. The software implementation of the solution being proof along with the unsolved CAD environment synopsis is widely used in the analysis of light propagation in optical wire gap. It is clear that so active a difference solution of equation using partial derivatives. The calculation will take a significant amount of time. This problem is particularly acute in the case of large computational datasets and used when simulating the propagation of radiation. These solutions are usually researched through parallel computing using the BPM method on multi-core processor architectures, including graphics processors. The results of recent studies in the field of block algorithms development for differential scheme demonstrate that it is possible to reduce the duration of calculations several-fold by improving calculation algorithms. Truth in case of the difference solution of Maxwell equations using a block algorithms, calculation are fast with using the hardware and intending difference scheme. That is, the algorithm of the method is modified. A new order for the math region nodes itself, but not the numerical method itself. All mathematical properties of the latter, approximation and stability, remain unchanged. The use of backing does not exclude the transition to parallel calculators. The blocking synthesizes block parallel algorithms of the FDTD method, which are more efficient than simple parallel algorithms. Therefore, it seems relevant to investigate the possibility of synthesizing a block algorithms of the FBPM method and measure its efficiency. The application of block algorithms of other numerical methods of computer optics, FDTD and different solution of a wave equation, has proved to be successful. The Fourier-Knowledge equation, where psi is a complex amplitude describing beaming around fields, and basic index of refraction. It is considered that in general the propagation of radiation is similar to that in a homogeneous medium with certain indicators, k wave number and n refractive index. For the purpose of this work, by reducing to the Schrödinger equation, considering the wave propagation of selected length in a homogeneous two-dimensional environment. Choosing from a variety of different schemes presented in post-Schrödinger equation, we restrict ourselves further to considering the simplest explicit two-layer schemes and implicit two-layer schemes, where the function defined on the grid area. In, in computational practice, we are solving using the BPM method. It is customary to use Crank-Nichols scheme. However, it is more appropriate to begin to construction of block algorithms with simple examples. Unfortunately, the authors could not find block algorithms for solving grid equations of two-layer difference scheme. They did not modify the scheme themselves. The aforementioned algorithms for solving the Maxwell and wave equations are based on three-layer scheme. A successful method for construction a mixed difference two-layer scheme for the head equation has been presented in Journal of Physics in 2019, volume 1368. The, the application of this method allows us to formulate a block algorithms for solving grid equations of mixed scheme. In the case of the BPM method considered here, a non-block algorithms for computing according to a mixed scheme written in Fortran is as follows. Now it becomes possible to organize a traverse of the grid region in which nodes inside the parallel-shaped blocks are sorted. This type of bypass is impossible for both explicit and implicit scheme. The similar form of blocks and the bypass rule characterize block algorithms for the difference solution of the Maxwell equations and the wave equation. Very similar algorithms, non-block and block, we provided for the head equation, albeit without software implementation, and were characterized by a five-fold acceleration in compilation speed, in comparison to the classical explicit scheme. A transition to the BPM method should theoretically be associated by discrete in this acceleration. Working with complex number leads to a twofold increase in the amount of communication between the RAM and the processor cache, and the number of arithmetic operations increases significantly. Consequently, the total duration for performing calculation will increase and the effect of blocking associated with a reduce in communications will decrease. Let us verify this assertion in practice. Experiments to investigate an increase in speed of the block algorithms were carried on the following hardware, software, and system basis. The results present in table. The acceleration decreased 3 times while remaining quite significant. New computational threads were now used to obtain the acceleration. The reduction in the computational time, according to the block algorithms, is associated with decrease in the intensity of communication between the RAM and the processor cache. The duration of calculations using the implicit scheme is characterized by great computational complexity than explicit scheme will be even high. At this time, such a scheme is absolutely stable, while explicit is characterized by an ultra-high stability criteria. As can be seen from the table, with the taking of the grid region, subject of the current criteria improved on the ratio of steps. The explicit difference scheme becomes unstable. The implicit difference scheme is stable, and the mixed difference scheme behaves like an implicit one. Moreover, with the selected parameters of the grid domain, the rule of solution module in the mixed scheme is much lower than in its implicit counterpart. This experimental result requires a theoretical interpretation that can be proposed in the future. This paper proposes a mixed difference scheme for solving the Fokker-Leonov equation using the BPM method, block algorithms for organizing calculation on it, and a block algorithm for an implicit difference scheme based on Jacobi method for solving linear systems. The effectiveness of the aforementioned algorithms and some properties of the different solution is demonstrated. The authors consider the result of the study to be primary and the effective to further transfer the methodology of construction block algorithms to more complex canonical scheme with widely used in the BPM method.